let's have a quick review. 4.2. Quickly. Vector spaces. Vector spaces. So how was that? Well, a vector space is built on a structure that's called a field. Now that's an algebraic field, not what a physicist calls a field, but what a mathematician calls a field. So a set K, or let's say a field, an algebraic field, but mathematicians just call it field. An algebraic field is a triple K plus times is a set K, all right, together with two maps and two maps plus takes two elements in K and maps it to K, and multiplication also takes two Ks and maps it to K, that satisfy CANI, CANI. So you saw this before, therefore I make it quick. The addition is commutative, it's associative. There exists a neutral element, let's call it 0 in the set. So whatever element in the set it is, we call it 0. And for every element, there exists an inverse. With respect to addition, the inverse being defined that you take an arbitrary element and you add the inverse, and then you get the neutral element. So you have to first write down this axiom before you write down that axiom. Now, it's also C times A times N times I times, but this only applies to the set K where you removed the neutral element of addition. Once you did this, then you have commutativity of multiplication, you have associativity, you have a neutral element, and the neutral element in that case we call 1. If it was named differently, we rename it 1. And then the inverse, and now you see why we had to take out the 0. Yes?
Why do we have to explicitly take out the 0? Can't we just choose to ignore it?
Yes, that is the meaning of taking it out.
Okay. I would still leave it in the.
How do you ignore it? You close your eyes when it comes along. Well, that's the close your eyes operator here. Okay. Okay. No, seriously. I mean, if you take 0, it doesn't have an inverse. So unless you take this out.
Okay. Right. Okay. For 0 itself. Right.
That's the idea.
Yeah.
Okay. Do I need to spell this out more, or is it clear? Okay? It's the definition of a field, and these are the rules you learned in high school. Okay, that's a field. Now, remark. A weaker notion to become, I should add wildly important, to become important later, namely when we consider modules, is a so-called ring. And a ring comes very much like a field. It is a set equipped with two operations plus and times of the same shape, but now this only satisfies CANI for plus, so it stays a commutative or abelian group with respect to plus. But of these guys here, the commutativity is gone, the associativity needs to stay, the neutral element needs to stay. Well, there are even rings without neutral element. So a unital ring, mathematicians would say. We take them with unit. And most importantly, the inverses are gone. So you no longer require these. Because you no longer require these, that means, of course, every field is a ring, but there are rings that are not fields. Okay. Example. First grade high school mathematics. You already know what negative integers are. You can add them and you can multiply them. That satisfies Caney. It would be commutative, so that would be a commutative ring. That's a special beast. Not special beast, it's a nice ring. It's a commutative ring. But famously, what is the multiplicative inverse of 2? It's 1/2. Map, it's not in there. Okay, so this guy is rings. So you actually, earlier in your life, learned how to calculate with rings before you learned how to calculate with fields. Okay, so rings are really simple. Okay, and this field is very special. And obviously stuff like R plus times, but also Q and so on, these are all fields. Very special rings. Okay, but that will become important later. Another example for a non-commutative ring would be the m cross m matrices over the real numbers, because you know how to add them and you know how to multiply them by matrix multiplication, say. You know matrix multiplication is not commutative, and you know not every matrix has an inverse. Namely, if the determinant is 0, it doesn't have an inverse. Okay? That means the m cross m matrices over R are a ring as defined here. Okay? So it's a very natural structure. You see rings everywhere. Function, well, we come to that later. Okay, good. So, but now we zero in on the fields, and then we have a definition, a vector, a K vector space. A K vector space where K is a field. That's important. A K vector space is also a triple, and now I circle the operations because they're not the operations of K. So the field K has operations plus and times, and this plus is not this plus, and this times is not this times. Full stop. Totally different structure. Okay, where these stay as they were defined before, where the plus, the circ plus, takes two elements in the vector space, makes an element in the vector space, and the circ times doesn't take two vectors and makes a vector. It takes an element in the underlying K, in the underlying field, and a vector, and makes it into a vector. Of course, standard example is a real vector space, is over the real numbers, where you can add vectors and you can have an S multiplication, which satisfy. Now there's a new set of rules. They're again Caney. Now I write them, okay, which satisfy Caney. And now it's K for the circ plus, A for the circ plus, N for the circ plus, and I for the circ plus. Exactly the same rules, but now applied to these vector space elements. It's the same laws, right? So I didn't spell them out before, I don't spell them out here. You saw all of this before. But then now for this times, there cannot be Caney because there are not two vectors taken. So there is another set of 4 axioms. And this A, well, you cannot really say for which operation they are, because all the operations, apart from this one, that is for the circ times, these axioms link these and these operations. So the associative law, you know how that works. Then there are 2 distributive laws, because you can distribute over this plus or you can distribute over that plus. Do you know what I'm talking about, or you want me to write it down? You know what I'm talking about. Okay, so these are the vector space axioms. Okay, full stop. So if you don't remember this precisely, go back to your linear algebra book and study this. Now you have a vector space, and you can define U, a subset of V, is a vector subspace or subvector space, the vector subspace, well, the V is a vector space, if for all U1, U2 in U, it's true that both their sum is again in U, and for all lambda in K, also lambda U1 is again in U. One also says a subset of a vector space is a vector subspace if the circ addition, the circ addition and the circ dot close on U. So you take two elements from U and they don't lead you outside there. You also saw all of this before. Okay? So from now on, drop the circles. Okay, we drop the circles, we write plus between vectors, but we must always know, is it the plus between elements of the underlying field, or is it the plus between vectors? Is it the multiplication of two k elements, or is it the s multiplication of a k element with a v element? And we can drop the plus, the circs, because the expression always tells you what it is. So for instance, if you have, e.g., you have lambda mu v is lambda mu v, where lambda and mu are from the underlying field and v is from the vector space. Now, what are the dots I left out? What's the dot in between here? Circ dot or normal dot? Tell me. Circ dot or normal dot between these two elements? Normal dot. And here? Circ. And here? Circ. And here? Also circ, because that makes it into vectors and so on and so on. So you can always see this, but they're really different operations. That we suppress the notation is a different issue. But now we drop the circs because I'm going to use them in a second for yet another operation. Okay, so now, as always, you now know, you classify these sets and so on by looking at the structure-preserving maps. And the structure-preserving maps, the homomorphisms, are called linear maps. So F is called a linear map, a linear map F from one vector space V in another vector space W. And now I should again emphasize this may be equipped with plus and with circ plus, circ times, and this is equipped with box plus and box times. Because the different vector space, it can carry different pluses and s multiplications. And a linear map is a map for which it's true, always true, that for all V, V1, V2 in V, it's true that f of V1 circ plus V2 is f of V1 box plus f of V2. So you can first add in the first vector space and then map the result, or you can map the individual vectors and then add in the target vector space and you get the same result, and that's a property of the map F. That's the additivity, and here you have for any lambda in the underlying field and for any v in the domain, you have f of lambda circ times v is lambda box times f of v. Okay, and you saw this before, probably without the circs and the boxes, but it's important to emphasize this once. And of course, it could be that W is the vector space V as a set. It could still be the same vector space as a set, and in principle, yeah, well, it could have different operations on it, so you still have to obey this. But of course, these two, the domain and the target, could be totally identical as vector spaces, including their operations, and then of course you do no longer need to distinguish, but that's kind of the degenerate case, not the rule. That's a linear map, and a linear map that's a bijection, and a bijective linear map is called a vector space isomorphism. And this is automatically linear in the other direction, vector space isomorphism. And again, call vector spaces W and V, including the operations, but I again suppress this, call them isomorphic as vector spaces if there exists an isomorphism F from V to W, and so on, and so on, and so on. It's always the same. This is, again, an equivalence relation. You look at vector spaces and you consider them the same if there exists a bijective linear map between them, and so on. It's always the same idea. Okay? These are those guys. Questions so far? Now, we come to a very important thing, and that is we can actually take all linear maps from V to W, define a new set, Hom V, W, that's a set, and as a set it consists of all the functions f from a vector space V to a vector space W, and in the future I will just put a twiddle on the arrow. Whenever I write a twiddle, I mean to say that this is a linear map. The twiddle means linear, because everything will be linear from now on, so that saves considerable amounts of chalk. As a set, it's this thing. Now the question is, can I make this set that consists of all linear maps between two vector spaces, can I make this into a vector space again? Yes, I can. Can be made into a vector space again, or a vector space, by defining, okay, diamond plus. Yeah, diamond plus takes two elements of Hom VW and maps them to Hom VW, and it does so by taking one and the other. It takes the pair and it maps it to some map that I call F plus G, but I have to tell you what F plus G means, where F plus G is again a map from V to W, and it's defined by taking a vector V and it maps it to F of V plus G of V. And this result we then call F plus G applied to V. And this is the diamond plus. And as you see, the diamond plus here is reduced to this plus, and this is the plus on V. No, that's wrong. That's the plus on W, because it's the results that I add up. Okay? So Hom VW inherits its addition from the addition of the target space by this definition, and similarly you get an S multiplication diamond dot for Hom VW. Now, I very quickly said where F plus G is a linear map. Well, I have to check whether this definition for the diamond plus indeed yields a linear map. And it does. It's additive. And in fact, the definition for the diamond times that I'm going to write down, or could write down in a similar fashion, indeed also satisfies this axiom here for linear map. So indeed, this is again a linear map, so it again lies in Hom VW. That's right. Now, at this point, if we hadn't taken a field here, but if we had considered a vector space over a ring, so if I remove the commutativity and the existence of an inverse element, I could still write down these axioms for a vector space, but now over a ring. That's a wildly different structure, and that is why we would not call talk about a vector space over a ring. It deserves an extra name. It would be called a module over a ring. But a module over a ring, which we're going to look at later in the course, is actually nothing but a vector space structure, but the underlying field is not a field, it's a ring. It's wildly different because you can go through all of this. You can do all of this also for modules over a ring until you come to this point. And if you come here and you want to show, well, I should write it down after all, that f diamond.g, you apply this to a v and you define this as, I'm sorry, not f diamond lambda diamond.g, and you define this as lambda times, and it's the times in the W space, g of v. Looks innocent enough. Can you show that this resulting guy is again a linear map? And the answer is no, because for that you should scale it here and pull the scaling out. You can do this, you can pull the scaling out, but you cannot pull it in front of the lambda because the scaling is a ring element, lambda is a ring element, but they no longer commute. So for a module over a non-commutative ring, you cannot make Hom VW again into a module. You simply cannot. You can only do that for a module over a commutative ring. It's a very small subtlety, but it plays a big role. And there are other, okay, so that's already the outlook. But here everything is fine. Hom VW can be equipped with diamond plus and diamond times and is then equipped with these operations, a vector space in its own right. So there's some terminology after all. Yes, please.
If you take the lambda, you have to take it out of the field underlying that could be V or W?
No, the field is K.
But it's the field under V.
Under W, under V, yes.
Under W.
They could be, okay, right.
And then you take lambda out of V and V
Okay.
is over R and...
No, okay, I see what you mean. Your question is, could there be vector spaces over different fields? Good question. Quick thought. For this Hom VW, okay, let's talk about this Hom VW. You're asking specifically here. We saw that the diamond plus is inherited from the target space plus, and so is the diamond S multiplication, because this is the S multiplication on W. And so what I should say is that a K vector space V and a K prime vector space W can be made into a K prime vector space Hom VW.
But where do you take the lambda from?
I just said. So if this is over K and this is over K prime, then the vector space I make out of this is also over K prime. Because you see the K prime you use here for the diamond S multiplication is the multiplication you take from the target space, because you already mapped. So you could generalize to this point. Yes, good question, thank you. Okay, so there's some terminology. As it is with terminology, it can be terribly confusing if you don't know it, and once you know it, it's trivial. So let's make it trivial. We talk about the endomorphisms over a vector space. That's the maps from V, the linear maps from V into itself. So these are the endomorphisms. On V, okay. Before the Hom VW were the homomorphisms. Then there is the automorphisms out V. That's a little bit more. That's the linear maps from V to V. So they are homomorphisms, but they're invertible. These are the automorphisms, or before we called them the isomorphisms. That's the set of isomorphisms. And we have those, yes. And of course, they are all vector subspaces. So out V is a vector subspace, and it's well, usually it's proper, maybe in some low dimension, in the lowest dimension. Let's do like this. So as vector subspaces of the endomorphisms. Well, they're linear maps from V to V, and they're invertible linear maps, and they're less invertible linear maps than they are linear maps. Full stop. Okay? And it's a proper inclusion unless the dimension is 0 or something like this. Okay, so that's the automorphisms. And then there is one very special, so that's one, that's another, follows this. And then there's yet another one, and that's V star. And V star is defined as Hom V, K. Now, the underlying field K is, of course, a K vector space in itself. Okay? It's a K vector space in itself, hence this makes sense. So here in this, K considered as a K vector space. And roughly speaking, the addition on the vector space is the addition on K, and the S multiplication on the vector space is the multiplication on K. Okay, and this is called the dual vector space. Dual vector space. And again, so because out is, lies in end, and end is a special case of Hom, of course this end and this out all inherit the just constructed diamond addition and diamond S multiplication of Hom VV. Hence, V star is not only the set, but it's the set equipped with diamond plus and diamond, my diamonds are not nice, diamond plus and diamond S multiplication. And this dual vector space will play an important role because from a vector space and its dual, next time we're going to construct all the, no, we have 3 more minutes, so we do it now. Definition. A PQ tensor T is a multilinear map, T that takes P copies of V star, P copies, and takes further the Cartesian product of Q copies of V and maps multilinearly in K. So now this thing means multilinear. And multilinear simply says it's linear in each entry. That is linear in each slot, independent of the other slots. So before, for the linear map, we had this additivity and scaling property. This now applies to each slot, and you have a multilinear map. And then we define V tensor, tensor V star. Now the order of unstarred and starred V's is different. We define this object. This is just a name. I just wrote down is the name. This is defined as the set of all T, where T is a PQ tensor. These are P many, these are Q many, where T is a PQ tensor. That's the set of all these PQ multilinear maps, and we can equip this with the pointwise addition and S multiplication. So what do I mean by pointwise? So e.g. T plus S, if they're both 1-1 tensors, so let's say for 1-1 tensors, T plus S, they then depend on what do they eat? they eat an element of V star, and they eat an element of V, there's a small v, and the sum of these two is then defined as T of sigma v plus S of sigma v, and this plus here is of course the plus in the target K, and similarly lambda T of sigma v for this 1,1 case is defined as lambda times T sigma v, and again this is the multiplication in K. And so then this space with this funny name, it's just a name. If you ask how is this symbol defined, I don't need to tell you. It's a name. It's a name. I could also call this identically. I could call it T P Q V. There would be an equally good name for what is written on the left, what is written here. It's just a symbol, but it's a symbol for that set equipped with this pointwise addition and S multiplication, and that's the PQ tensor space over this vector space. And there we will take off next time. Questions? Yeah?
For this remark about the HOM VW, is it really possible that there are different Ks?
Okay. Let's revisit it. Yeah?
V from K, from the underlying field K, and W from K prime.
Okay.
And what means linear? Because in the definition of linear on the left, the lambda one uses the circle multiplication and the box multiplication, but it has to be the same lambda from the same field.
You're absolutely right. You're absolutely right. Right. So here it would work, but then where it doesn't work anymore is what this linear means if these are not the same fields, because here it's the same lambda and you cannot switch. You're absolutely right. Thank you very much. So in principle here it works, but then from here you have K must be K prime. Yes. Yeah, you see, I didn't even consider it in the beginning, but then the question actually made me consider it. It was very clever at this point, but it fails at this linearity. That linearity forces you to have K equals K prime. Thank you very much for pointing that out. So in our discussion of vector spaces, we arrived at the point that we constructed the space of PQ tensors, TPQ, which over a vector space V we assumed as given, and this also had the name V tensor product V ... P copies of the V, and then there's another tensor product symbol, and then there are Q copies of V star, and all of this is just a symbol. And it's defined to be the set, first of all, the set that contains all multilinear maps that start from P copies of V star. So you see you have P copies of V here, but the map goes from P copies of V star and Q copies of V multilinearly. So also multilinearity will be indicated by a twiddle in the basic algebraic number field that underlies all of this. And now if we define a set like this, as you know, so the multilinearity is like a condition we impose. Instead of writing this, I could impose the condition that these maps are multilinear. And as you know, if you want to be sure that this is a set, you need the principle of restricted comprehension. So you ought to say from what set these elements are taken. And so that's a general question, and I will not every time write this down, but the basic idea is if you say you consider maps from A to B that may have some additional property or not, then by the principle of restricted comprehension you need to say where these objects come from. And now you remember that I put quite some emphasis on the fact that this notation for a map is just hiding the fact that a map is always a relation. And the relation is, after all, is a very special type of relation, namely a functional relation, but the relation is always a subset of the Cartesian product of the domain and the target. So these objects are, although it looks funny formally, but if you go back to the definition of maps that we wrote down, then the restriction is that the whole thing ought to be an element of the power set of A cross B if F is a map from A to B. All right? So that is how the principle of restricted comprehension tells us that actually what I'm constructing here, the PQ tensor space, indeed is a set. So that whole thing is a set, so that's the definition as a set. And then we can equip it with addition and multiplication. I have an addition that takes a PQ tensor, that takes another PQ tensor, and produces from it a PQ tensor over some given vector space V, and that is defined pointwise. So it's the addition on tensors is the addition of these maps as it's defined pointwise, and there is an S multiplication that takes an element of the field and together with a PQ tensor produces a PQ tensor as usual. So that's this, and hence this space TPQ over some given vector space V equipped with these two operations is a vector space. In order to check this, of course, you have to check whether it satisfies the 8 axioms: commutative, associative, neutral, inverse, another associative law, 2 distributive laws, and the unitary law. So the tensor space is a vector space. Now, how do we construct new tensors out of old tensors? There's several ways. The most important one is the so-called tensor product. And unlike the addition that takes two tensors of the same valence, so this pair PQ is the valence of the tensor. Sometimes people call the sum P plus Q the rank of the tensor. And now the tensor product takes a tensor T of valence PQ over some vector space and another tensor S, which may be of an entirely different valence, let's say that valence RS. Then the tensor product of T and S is this gentleman, and so this is a double working of this symbol. Up here we use this symbol as mere notation, so let's say that's the orange tensor product symbol, and that just indicated via this definition this set. Now here we're using the same symbol again, but it's different. It's the tensor product between two elements of such a tensor space, so it should be called the blue tensor product. And this tensor product is then, by definition, a tensor of valence P plus R, Q plus S over the same vector space, and it's defined quite simply T tensor S. Now, T can eat up P vectors, so that's a vector V1 to Vp, so these are not components of a tensor or a vector. We've never talked about this so far. So these are individual vectors. They're called V1 to Vp. But then the S can eat R of those. So we have further Vp plus 1 to Vp plus R. And then we can eat Q plus S covectors. So let's call a covector denoted by an omega. This is omega 1 to omega Q, omega Q plus 1 to omega Q plus S. And so if you plug these in, it's the P plus R, Q plus S tensor, you land in the field. So on the right-hand side, we need to write down a number in K, and that is simply T eats up as many vectors in that order as it can, V1 to Vp, and then it eats up as many covectors as it can, omega 1 to omega q. That's a number. And now we have here the multiplication, which must be the multiplication in K, of course, and then the S eats up the rest. It's the Vp plus 1 to Vp plus R, and the omega q plus 1 up to the omega q plus S. And this is the tensor product. That's very simple. So that's one important way how we construct new tensors from given tensors. Now, however, examples are in order for tensor spaces, and we start with the T01 tensor space over a vector space, and let's see what that is. So T01, that is, according to our notation here, just to practice this a little, this is just a V star, isn't it? Yes, it's just a V star, so there's no tensor product, so that looks good, okay? So if that's supposed to be the case, then better, this is just notation at this point, and this is all the T's that start in 1V and multilinearly go to K. Oh yes, we agree that is indeed our definition of the V star, so this notation is consistent with what we defined before. That's pretty obvious. So the 0, 1 tensors are just the dual vectors, are just the dual, the whole space is the dual vector space. And the 0, 1 tensor is a covector. That's another name for a tensor in the dual space. So in physics, we call these guys often covectors. Now, what is a vector and what is a covector depends on what you call a vector and a covector. If you call the elements of V vectors, then those are the covectors. For finite dimensional vector spaces, we can turn this around. I'll come to that in a second. Okay, so first thing. Now, it's also illuminating to look at the 1-1 tensors over a vector space. So according to notation, that would look like this, right, wouldn't it? And that, again, is just notation. So I should rather say, so this is definition, so I have this triple. It's just another symbol for the same thing. And actually, the definition starts here. So those are all the multilinear maps. Now you've got to turn this around. V star and cross V multilinearly in K. And the question is whether we already know such objects. And I now claim, and I'm going to show this, I now claim that this is actually the same as the, no, endomorphisms is wrong. No, it's true, as the endomorphisms on V star. So V star is a vector space, and you can look at the endomorphisms on V star. So how do you see this? That multilinear maps, a bilinear map from V star across V to K is the same as this. Well, the idea is for every such bilinear map, construct an element of end V star and show how to recover precisely the map you started from the map you constructed. Then that means you can go back and forth. It contains the same information. You can map this 1-to-1, and you have to check that this is, as a vector space, the same. So you not only have to construct a bijection, you have to see that it's linear in both directions. But that's very simple. So I start, so given a T in V tensor V star, so such a guy, you construct a T hat, let's call it T hat, which is now an element in end V star, as follows. What do we got to do? Well, an end, that means that T hat is a linear map from V star to V star. That's an endomorphism. So to every omega element of V star, we must assign another element in V star, and I would like to induce this map from a given T. And I do this by employing the T up here. And the T up here has the nice property that if I fill the second slot with this omega, I satisfy this, then all that's left is an object into which I can plug in what? I can plug in a vector and I get a number. But an object into which you plug in a vector and you get a number, so that's a map from V to K, but because it's a linear map from V to K, obviously, because if you have a sum here or you scale it, it's linear, but such a linear map is of course the same as this whole thing being an element of V star. Oh, very good. That is what we wanted. We wanted an element of V star. So from a T, we construct a T hat. The question is, do we lose information? No, we don't, because we can reconstruct the T up here. What is a T? I need to give you a V and an omega, and you reconstruct this simply by employing the T hat, which I just constructed. The T hat eats an omega and results in an object, namely this one, that lies in V star. But if it lies in V star, it can act on the V and you get a number. The question is this number the original T? Well, yes, it is, because you can really reconstruct, because you use the definition. This is, by definition, T of V and W. Oh, yeah, you reconstruct it. So it means you have as sets, you have this here bijectively, and the question is it linear? Well, you check this is also linear. So we saw that the 1-1 tensors over a vector space are isomorphic to the endomorphisms on V star. Now, you might also feel that it might also be the same as the endomorphisms over V. But this is generically not true. So we have the following questions. I continue here. The following questions. So I would like to continue this list, and in particular, we had the 0-1 tensors. Now you look at any physics textbook, it will tell you that the 1-0 tensors, they're actually as vector space. A tensor space is a vector space, so it makes sense to write this isomorphic as a vector space. It will tell you that's the same as the vector space itself, whereas the 0-1s were the duals. But the question is this really true? And the answer is, in general, it is not. Then another member of the list could be, again, the 1-1 tensors. And the question is, aren't those the same as the endomorphisms over V? Well, yes, but not generically. Okay. And finally, and that's actually the fundamental question that links these two, that answers the question. Okay, so this is the key thing to check, is actually if you take the dual and then you take the dual of the dual, is it actually true that you get back the vector space? And again, here the answer is no, that's not always true, but it is true if we have a finite dimensional vector space. And that we're going to look into that in a second. Now, we haven't defined yet what the dimension of a vector space is, so that's something we need to do. And only if we have a notion of dimension, we can start restricting the dimension to the finite dimensional case. Now, here some care needs to be taken in the definition of dimension. In particular, what we're dealing with here are bare vector spaces. We have no additional structure assumed. We have no norm on the vector space. And if you have no further structure than the vector space structure, the only notion of basis you can define is a so-called Hamel basis definition. So if V plus S multiplication is a vector space, then a subset B of V is called a basis. But in order to not cause confusion, we call this a Hamel basis, called a Hamel basis, if A, every finite subset if it's finite, we can name the elements. We call them B1 to B capital N, natural number. Any finite subset of B is linearly independent. And you know what that means? That is, so linearly independent, it can be yes or no, true or false. And this condition is, let's write it like this, by definition, linear independence is sum from I equals 1 to capital N, lambda I bi equals 0. Well, for future use, we'll write the index up here. This implies lambda 1 equals lambda n, they're all 0. Now you see this is an application of our insight that this is a proposition, this is a proposition, this is a binary operator, so everything in the box is a proposition. So what is in the box? The box is either true or false. And the truth or the falseness of this box is equivalent to this thing being linearly independent or not. Okay, so this is something that in high school causes students usually great pain to evaluate this, and that is mainly because they haven't had a proper explanation of the implication error. Okay, so it's linearly independent, and what I would like to draw your attention to is here, we only look at, I mean, every finite subset of the basis must have this property. And the finiteness is important because then we have a finite sum. If I had defined there is a basis if all the elements in B, well, are linearly independent, I have two problems. First, B could be overcountable, non-countable. If it's non-countable, you can't write down a sum in the first place. You can't even write down a series, because the series requires that you have partial sums. So if you have an uncountable basis, that wouldn't be possible. But even if you have a countable basis, this would result in a series up to infinity. But if you want to know what a series does, you need to have a notion of convergence, because there's a limit involved. Well, if you have a vector space without additional structure, not even with a topology, you cannot talk about convergence. So on a bare vector space, the only thing you can do, you can check whether for every finite subset this is true. And condition B, so that's the generating system property, and B is that for every element V in the vector space, there exists a finite set, let's call them V1 to V capital M, and those are all elements in the number field, such that the vector V may be written as the finite sum I equals 1 to M Vi Bi. There exist these guys, and there exist as well B1 to B capital M elements of this B, again a finite subset, so that the vector can be written as a finite linear combination, but the guys you choose to construct the linear combination, they may be taken from the possibly big space B. And this is called a Hamel basis. Now, if you remember some Fourier analysis or something, there you have Fourier series, there it goes up to infinity, and you say, well, you have an analytic, not analytic, you have a Fourier expandable function, then you have the cosines and the sines over the real numbers, right? They're countably many. Yeah, that's a basis, but it's a countable basis. It's not a finite basis. And you can actually do this Fourier analysis with this countable basis, but only at the cost of having Fourier series. So obviously the cosines and sines in Fourier analysis do not constitute a Hamel basis. I think they constitute something that's called a Schauder basis, but then you need to have a notion of convergence, so you need more structure on the space you're on. And the Hamel basis for these Fourier expandable functions would actually be uncountable, whereas the Schauder basis is countable, and one uses the Schauder basis. Okay? So this, however, is the notion of basis for very general vector spaces with no further structure assumed. Well, you can then define, and in fact there's something to prove, but we're not going to do that, define the dimension of the vector space. The dimension of V is the number dim V, and it's defined to be the cardinality of the basis. So that may be infinity, various infinities, but it may also be finite. Okay. So now we have the theorem. And this theorem you're asked to prove on the problem sheet, the upcoming problem sheet. The theorem is that if dim V is less than infinity, so if you have a finite vector space, then V star star is isomorphic as a vector space to V. And so we have the remark. If you have V and you look at V star, then you could identify V with V star star if you're finite dimensional. And that means you could call the elements of V vectors, and then you call the elements of V star covectors. But this is a vector space, so its elements could also be called vectors, and then the elements of V would be the dual of those vectors. Those would be the covectors. Okay? So in finite dimensions, what is a vector and a covector? You could turn this around, and we will have opportunity, however, in manifold theory to think of tangent spaces as the vector space, and then over the tangent space we construct the covector space. And so usually one then has this conventional asymmetry. One calls these guys vectors and those covectors, but you need to know that you start with this V space. It's no problem in practice, but once you start thinking about this, you might get confused. So I try to confuse you beforehand, and then maybe the confusion, I don't know whether that works pedagogically, but what I said is true. Okay, good. So then we can go back to this, and once we saw this, that the V star star is again the V, you can redo this construction here, but you can do it from V to V, and you will very quickly see that if you use V star star V, that from this one immediately you have this, and from this one you also immediately have that, and you know only, yes, but only for finite dimensional vector spaces. For finite dimensional V. So that's the caveat here, and we want it to be a little precise. Now, so far, our choice of basis or our considerations of bases have only been used to classify vector spaces into finite and non-finite dimensional ones, but bases have another property, and you of course know that already. Once you have a basis, instead of talking about the vector, which is a rather abstract concept, an element of a vector space, that might not be very enlightening if I tell you, take this vector V and take another vector W. And then you ask me, which V and which W are you talking about, if I want to give you concrete vectors? Well, I say, well, this one and that one. Well, that's not good enough. What one usually does, one agrees on the basis, and then I hand you a particular vector by handing you the so-called components V1 to Vm with respect to that basis. I can hand you another concrete vector by handing you the components of that other vector with respect to the basis. Okay? So bases are used to communicate which precise vector you mean, but it's always subject to your choice of basis. We have to agree on that. And, but however, there's a warning. If you want to understand the theory and the constructions, there are things, if you have a if you have the components of a vector, and you start defining new objects, and you define them in terms of components, there is a danger. And the danger is that you do illegal constructions that are not good in vector space theory, in particular constructions that would take a very different shape if you changed bases. So the general rule is really always construct everything you want to construct without choice of bases. Okay? And only once you constructed it without choice of bases, then you may introduce a basis to study what array of numbers do I need to provide in order to provide this new object. Okay? Always try to do construction basis free. So some people say a gentleman only chooses a basis if he really must. Okay? And that's it. So only if you have a concrete reason to choose a basis to calculate something, but construction should be basis free. Now, once we have a basis, for instance, we can define what we mean by the components of a tensor. So the components of a vector, I already said what I mean, but this can be generalized. Definition. Let T be a PQ tensor over some vector space, and let V be finite dimensional. So from now on, let's only talk about finite dimensional vector spaces. So now let B1 to B dim V be a basis of V. So you choose a basis of the vector space. It turns out that induces a basis on the tensor space, but first we define the components of the tensor. So the tensor is an abstract thing. It's a multilinear map. And the components of a tensor, they're not so abstract. It's a PQ tensor. So the components are numbers, but there are a whole lot of numbers. They're numbers T, A1, AP, B1, B. Okay, let's call this basis small e. It's also more standard. B1 to BQ. And these are numbers. And these numbers are defined by taking the tensor, which is a multilinear map, and plugging in, oh, I see, I forgot something. Anyway, I write it down and you'll see how it works. And I plug in epsilon A1, comma, epsilon A2 to epsilon AP, comma, EB1 to EBQ. And this is the basis E. And the epsilon is a basis, so let's say epsilon 1 to epsilon dim V star. But dim V star, because it's isomorphic to dim V, the finite dimensional, it has the same size. This is the basis of V star. So you choose a basis on V and you choose a basis on V star, and then you can define the components of any tensor. And you see all these components are numbers in the underlying field, say the real numbers. Those are the components of a tensor. However, remark, usually one does not choose independent bases on V and V star. You can do this. These are two vector spaces. You can choose a basis here, you can choose another basis there. But usually one chooses on V star a basis that is induced from a previous choice of basis on V. By what condition? By the condition that the eighth basis vector of V star is a covector, right? As a covector, it can eat a vector. For instance, it can eat the bth vector of the basis of V, and you require that this be delta AB, where delta AB is just a symbol that's 1 if A equals B, and 0 if A is not B. And this is a linear relation, and it has a unique solution. So for every choice of basis on V, if you impose this additional condition, you get a unique basis on V star. Why would you impose this condition and not another? no particular reason, but if you have to make a choice, make sure that you don't make choices all over the place. If one choice can already be used to imply another choice, it's usually most efficient to keep the number of your choices minimal. Although you could argue that imposing exactly this relation makes the choice once and for all, makes the relation once for all. Anyway, it's a very convenient induction principle for a basis here from a basis for a basis on V star from a basis on V, because many calculations actually simplify because there's so many zeros around. That's the basic idea. And the such induced basis is called the dual basis. Okay, it's called the dual basis on the dual space. The dual space. So what the dual space is, you already know, that's the V star. And the dual basis, that has to do with this condition. That is, this dual is called because of this dual, and this is called dual because it's the dual space. It's the dual basis of the dual space. So you could choose not the dual basis of the dual space. You could choose just a basis of the dual space. But we choose the dual basis of the dual space. I will not go into that detail in the future, but it must be said once. Okay, now the most important thing here, however, is I can define components, and you say, very pretty, but what do you do with them? And the answer is, once you have chosen a basis and you have a tensor and you know its components, you can reconstruct the abstract tensor from its components. That's the whole point. So the components suffice to determine the tensor. So reconstruction of T from its components. And it works as follows. You take the big guy T, and you take its components, TA1 to AP, B1 to BQ. Those are numbers, right? So, you know, the blackboard went on. I would put now a multiplication here. The multiplication is, no, that's wrong. Hang on a second. I'll tell you in a second what the multiplication is. It's actually in the tensor, it's the S multiplication in the tensor space. Anyway, and then I write down EA1 tensor, tensor EAP, tensor epsilon, yes, epsilon B1, tensor, tensor epsilon BQ. Now, which tensor symbol is this? Is this the blue or the orange one? Well, we know that this is a vector because it's an element of a basis, but that means it's, in particular, it's a 1-0 tensor, and those guys, in particular, every basis vector here is a 0-1 tensor, and for PQ tensors, we defined the tensor product. So it's the blue one, right? So this is the blue tensor product here. So in particular, without this, if I just take this last line, this string here, what type of tensor is this? Well, it's a PQ tensor. Okay, it's a PQ tensor. Oh, like our T, that's pretty. It's a PQ tensor, but there are actually many PQ tensors. It's a PQ tensor for particular choice of A1 equals 7, AP equals 28, B1 equals 1, BQ equals also 1. But I put here, so, okay, line. I put here the S multiplication, and this is the S multiplication of TPQ over V, because I have a number in the field and I multiply it with a given tensor. That's our S multiplication, third line from above here. Okay? That is this. Okay, and now the question is, does this really recover the tensor? Well, you can check by evaluating the tensor on an arbitrary vector, and you need to know how the E's and the epsilons act on arbitrary vectors and covectors, which you do by expanding them themselves. So proof that this recovers is essentially, it's very basic, and it's a finger exercise on the next problem sheet. This recovers. This is indeed T. So this equal sign here, is correct. Because it's in every textbook and it has practical importance, let's briefly talk about the change of bases. So again, we have finite dimensional vector spaces. So say E1, so let's say E1 to ED, and let's call this dimension D for short. E1 to ED is a basis of whatever vector space we look at. Then, of course, we can construct a new basis. Let's call it E A twiddle for A equals 1 to D. It will have the same number of elements, and these will be vectors again, right? If these are vectors, each of these vectors can be expressed as a linear combination of the original basis, because that's what a basis is. It takes a vector E twiddle, and you can express it with components, which I now call AB, in terms of these guys, and you take a sum over B equals 1. I should have said this before. I'm sorry. Okay, I continue, then I'll tell you something. B equals 1 to D, you take the sum, this is a linear combination, and of course you have to do this for every new vector, so actually you have components for every A, so this object gets 2 components. So these guys here, they're just elements of K. This here is the S multiplication in V, okay, and that is the new basis. Now, not every such linear combination will lead to a basis, because you can easily destroy. Can you destroy the linear independence property this way? No, you cannot do. But you could you could destroy that too. That's true. You could also destroy the linear independence and the generating property. So the point is, there is a condition. You need to be able to also recover the old basis EA from the new basis E twiddle, and let's say that is by coefficients B, BA, and there's a sum B equals 1 to D. And if you can do that, it's easy to check that if this is both possible, then B as a matrix, if you wish, is the inverse of A. Okay. That's this, but we'll talk about matrices in a second. There's something else I forgot to mention before. Maybe you saw it before, that's why you didn't complain, but there is an aside on notation. As we saw before, when we reconstructed, so when reconstructing T as TA1 to AP, B1 to BQ. Some space here. I wrote EA1 tensor ... tensor EAP tensor epsilon B1 tensor epsilon BQ. Actually, what I forgot over there, but that's something I will from now on systematically forget, is a succession of P plus Q sum symbols. Namely, the sum runs A1 equals 1 to the dimension of the vector space. That's this A index we're summing over. A2 from 1 to D down to B1 from 1 to D, which is also a dimension of the covector space. And these are, so BQ, these are P plus Q sum signs. Okay, they must be there because, yeah, you sum over all of these. This is the expansion, and I forgot to write down the sum signs on the previous blackboard. However, I forgot so because it's convention to forget them. We do not write them in the future because every time there is an up index and a down index, there will be the understanding, unless something else is explicitly said, that they are being summed over. So whenever you see an up-down pair, you sum over it. Now, you might wonder, how does an index deserve to be up and how does it deserve to be down? So the up-down convention is the following. There's only one choice and all the other choices follow from it. So the fundamental choice or fundamental convention is the following, that the basis vectors of V, basis vectors of V, not vector, basis vectors of V are labeled by a downstairs index. And that is what I did. So I wrote E1 to E sub D. Those are not components. Each of those is an element of V. It's the first vector, the second vector, it's the dth vector. That is the fundamental convention. Well, and basis of V star by upstairs indices. So epsilon 1, and I did that as well, I just didn't talk about it. Epsilon 1 to epsilon d, those are all elements of V star. So why does everything follow already? Well, remember what the definition was of these tensor components. The definition was you take the tensor, and the tensor eats, first of all, those covectors, but they have their index up, you see. The covectors it eats first, they have their index up. So the resulting object, the resulting component also has the indices up. So if you're on two sides of an equation, you always want to have the upstairs, downstairs level matched. But the component that corresponds to this first entry has its index up because the basis vector you put in according to the fundamental convention has the index up. That's nothing you have to memorize on top. You just have to memorize here the fundamental conventions. Okay? And these indices are down simply as a consequence of these indices being down. Okay, and everything else follows. And then it's clear if you reconstruct, it will already be in position. Okay, so actually the backbone of the summation convention is that we don't write these sums, and always when we see an upstairs, downstairs index pair, we sum over it. Okay, same index up and down, and this is sometimes called the Einstein summation convention. Summation convention is omit the sigma A equals 1 to D if A appears once up and once down. If A appears as an upstairs and a downstairs index in the same product. Product in a generalized sense, of course, not if it's in a sum, if it's in a product. Now, there is one remark, again, with conventions, you could easily think, oh yeah, let's always do this in all branches of mathematics. It's a good convention because it saves chalk. But in fact, the convention only works, remark, convention only works with linear spaces, and in particular linear maps. I provide one very basic example, which, however, says it all. So imagine you take a linear map F, or let's call it phi, from V to V. Well, we know that this phi actually corresponds to a, well, let's be not so, one could start from here. Let's take a phi that goes from V star cross V into K, multilinearly. So let's let phi be a 1-1 tensor. Now, if I evaluate phi, I can plug in some covector and some vector, and I will get a K. So if this is an element of V star, and that's an element of V. Why? Well, because that is what a 1-1 tensor is. Now, the business with the indices starts if I have a basis. So if I now choose to write the omega, the covector, in a basis, how do I do this? Well, I need to choose the basis on the covector space, but that basis has its indices up. But then an omega has components omega A, and the reconstruction theorem previously written down for general tensors on the covectors works out like this. And the V is expanded similarly, but with the basis on V. According to the fundamental convention, the basis vectors are labeled down, and that means that the, oh sorry, I choose a different dummy index. B, again up, down, they're, according to the summation convention, they are contracted, okay? But we can, with invisible chalk, in this case orange chalk, we can write the sums for clarity at this stage, B1 to D. Okay, so you don't need the, if you're blind to orange, then you need to use the summation convention. So what am I driving at here? I just expanded these objects here in terms of the basis and the co-basis. But now we know, because phi is a multilinear map, I know I can pull out this first sum. Is that correct? Because the finite sum, multilinearity, includes additivity in this slot. Additivity means you can pull out sums. So I can pull out the first sum, A equals 1 to D, and I'm left with phi of omega A epsilon A, but the sum is taken outside, that's fine. I can also pull out the second sum. So I can first leave it, and then in the next step, but I do this in one step, I can pull out the second sum from the second slot, and I have VB EB. That's all fine, okay? And if you now wish, you can also pull out, and remember, so these VBs here, they're all elements of K, and so are the omega A's, but these are elements of V star and V. Now, you could also, by linearity, pull these guys out, and they go here. Let's do that. So that's the sum, A equals 1 to D, sum B equals 1 to D. Then you pull out the omega A and the VB, and you're left with phi of epsilon A and EB. But this phi here is nothing but the components phi AB. So what you arrived at is abstract object phi, 1-1 tensor, an abstract object omega, a covector, abstract object V gives you a number. The question is, what is this number? Well, forget about the abstract objects, equal, equal, equal. You take the if you choose one basis in V and the dual basis, you take the components of the vector, or you take the components of the covector, and you take the components of the tensor with respect to a given basis are all numbers. And you build this big sum and this product, and the result is this number K that comes out if you plug in omega and V. So that's the idea. You can have components, and the components have all the information. And this is how you usually work in introductory physics courses. You take vectors in their components, you take linear maps in matrices. I'll talk about matrices in a second. This is a matrix of objects, and they normally would say you come with omega from the left and with V from the right. I'll talk about this in a second. That's this, but what I want to drive at is, imagine now you are not colorblind, you don't see orange. If you don't see orange, what's the difference between the first and the second line? What's the difference between this and this if you don't see orange? Nothing. right? It's nothing. But this equal sign is not for nothing. This equal sign is because of the linearity of phi, isn't it? I can pull out the orange because phi is linear. So if you choose to omit some signs, that's fine, but an invisible sum sign can be invisible here or invisible there. That's the point of invisibility. You don't see where it is. But if it can be invisible here or invisible there, then better the map be linear, because otherwise it makes a difference where you don't see it. And because you don't see it, that would be a problem. Okay? So that's the whole point. The summation convention only works when it plays with linear maps. If you play with polynomial maps, like in algebraic geometry, and you use the summation convention, at least in unclever ways, you're in trouble. That's my point. Okay, so let me make a few more polemic remarks about matrices. Remark. So having chosen a basis in V and a dual basis in V star, the basis will always be the dual basis unless I say something in particular. It's very tempting. And you see, if in the mathematics lecture, which has nothing to do with temptation, the word tempting comes up, of course, you've got to be careful, okay? So it's very tempting to then say, well, an omega, which is a covector, can be expanded as omega A epsilon A using the summation convention. But because the basis is chosen, so this is fixed, this guy is fixed, it's very tempting. So the tempting part is this one. It's very tempting to think of the omega, I put in corresponds to symbol, to think of the omega as a collection of its components. And so you write them down like this. Okay. Similarly, if you have a vector, which of course you can expand like this, there's nothing wrong about this. This is fixed. Okay, that was the arrangement. Well, if it's fixed, then it's very tempting to say, well, the vector really is. And now that I write this as a row vector and this is a column vector, is already part of the Witch mathematics that is about to come. But you've seen this kind of Witch mathematics before. You say the vector actually corresponds to the components. Yeah, we have the basis in mind, but it's these components. And the covector we write as a row vector. Well, it's just convention. Yeah, you can do this. Now it goes on. You can take a phi, which is an element of end V. So you can take end V, take a linear map on the vector space. That's, of course, the 1-1 tensors over V, as we said. And you take a linear map. Let's call it phi. Now we know that this phi can be written as phi AB EA tensor epsilon B. Okay, so that's what we showed before. You can do this, so this at least as vector space is isomorphic. And then it's not only very tempting, but it's the basis of any engineering mathematics that you say you think of the linear map. You think of the linear map as such an array, in this case a square array, where the 1-1 component is here, the 1-2 component is here, the 1D component is here. So the first line always has the 1 here. And then this continues with phi 2-1 is here, and so on. It goes down to phi D1 is here, and it goes up to phi DD. And so the D up is in the last line. And sometimes one says this is the convention that if the object has two indices, the first one and the second one, that, well, that you say this is the row and this is the column. So you take the one element and you put it in row 1, column 1. You take the 1, 2 number and you put it in row 1, column 2. It's this row column rule. Now, the polemics I want to convince you of, that we should all be polemic in this way. This is just one way to arrange the information in here. You have d squared many numbers. And one way to arrange the information in there is like this. As much as this is one way to arrange d numbers, that's another way to arrange d numbers. So what we do here on the right-hand side are just conventions of how to arrange numbers. And so some people call this a symmetry of numbers. So if you go to a cemetery and you look for your great-great-grandfather, I choose this because you have no emotional attachment to him. So your great-great-grandfather, where does he lie? He lies in row 7, column 5. That is where he is. There you find him. Of course, it's pure convention. If they run another scheme, he lies in, you know, okay. It's pure convention to do it this way. Aha. What does that imply? Well, if you choose this convention, then you can do the following. So if we consider two endomorphisms, phi and psi, they're both endomorphisms on the same vector space, and then we can look at phi after psi. Well, phi after psi will be again an endomorphism on V. It's the composition of two linear maps. It's a linear map, okay? But now, if that is true, it should actually have a basis. Well, it's an NV. You can also think of it as it has components given like this. But this may be confusing because you think if it's in NV, it only eats a vector, but then you define this guy. You say this is a tensor. You define by saying this epsilon A acting on the result. Okay? So that is this. And now you want to figure out what that is, so let's write it down. It's epsilon A. That's phi of psi of EB, no doubt. What is that? That's epsilon A is phi of, what's psi of EB? Well, psi of EB is psi m b e m. That you can quickly check from what was said before. Now phi is linear. These are just numbers, but phi is linear. There's a sum. I can pull the sum out. Well, it's invisible, fortunately. We don't need to explicitly pull it out. We pull it out invisibly. And then we pull out the numbers as well. So this epsilon A, psi mb, they're just numbers. And all you're left with is phi of em. But then the epsilon A is just a covector. So it's a map from vectors. It's linear. So again, you can pull out the numbers. So you end up with psi mb epsilon A of phi em. But we said this epsilon A phi em is just a way to talk about the corresponding tensor phi that has an epsilon A em. So what you really have here is psi mb times phi, and now something went wrong. No, it's correct, times phi am. And what is the multiplication in here? It's the multiplication in the number field k. Okay, that's all very simple. And this is true, but if this is in k, k is a field, so it's commutative. So in particular, this is precisely the same as commuting to the two factors. There's no difference between this. On the left, on the right, it's the same thing because these are numbers. But now, once you start looking through your graveyard glasses, you say, I like the second order better, because once I have the second order, I can have the additional rule that I want to have indices that are close to each other and I sum over. And then I have here, this is the row, this is the column for the numbers representing the first endomorphism, phi after psi. Here I have again the row and the column of the numbers representing the second endomorphism. And what do I sum over? I sum over this index that gives this column and this index that gives this row. So if I actually calculate this, what do I do? Well, you sum over these guys here. And what's the left-hand side here? Well, okay, it's all equal. So the left-hand side here is phi after psi, can be considered a 1-1 tensor with indices A, B. Aha, in the 8th row and the bth column, if you choose this symmetry convention, 8th row, bth column, lies what number? Lies this number that you get this way, but then you see you run over the columns, but you fix the row. And in the second matrix, you fix the column and you run over the row, and that is the standard rule that if you have the symmetry for phi and the symmetry for phi, that you do row times column, or you can even write it down like this. You probably saw this before. So this is the symmetry for phi. This is the symmetry for psi, and you go over the row, and here over the column, and the result, so there's an equal sign in between here, the multiplications between this one and that one, then you land here and this here, and you get the rule row times column for matrix multiplication. And then you say, I now choose to only write down the symmetry. Let's give it, I don't know, the symmetry has flowers, so there's a flower on top. The symmetry for this, and I write down the symmetry for that. And I define a new rule that is this row times column rule. This is matrix multiplication. And the whole point of matrix multiplication is it's actually the symmetry rule for finding the representing symmetry for the composition. This is the deep reason behind row times column. But it relies on this additional construction here. Now, if you use this rule and you extend it to Hom VW with corresponding dimensions, then you can also act with an omega from the left on a V. So with this rule, I write it down here. So I derive the rule from here, but you can also say you have an omega and it acts on a V. Without coordinates, without basis, it's clear this is possible. This is a covector. A covector acts on a vector to yield a number. That's the definition. Acts on a vector to yield a number, but that's omega A, epsilon A, VB, EB. You pull out the sum that's invisible, you pull out the numbers, VB, and they have epsilon A, EB. And now, if you have chosen the dual basis, this is a delta AB. And if this is a delta AB, then this double sum over A and B yields omega M VM. And if you then have this as a row and this as a column, you can think of this again as the symmetry representation with the flower on top. And you again have here the matrix product. Okay. And then you end up writing stuff like it's written here, which without the summation convention is omega A. Now these are all numbers. These are numbers, so I can write them in a different order. Phi AB, VB. You say, there's a matrix multiplication here if I write this as a row, and there's a matrix multiplication here if I write this as a column, and this goes on to be written as omega transpose, because you want to emphasize that you do this. Then comes the phi, which is a matrix. So these are all the symmetry representations. And then comes the v. And you've certainly seen things like this. And this transpose makes you think that this is some good object, the transpose. The transpose is not a good object at all. Okay? It's very bad notation. It pretends to be, it almost pretends to be basis independent, but it is not at all. Okay? So you might think of this result, say, oh, omega comes from the left and v comes from the right, and I calculate this like you do in the introductory course. Okay? But this is, I mean, it's not necessary, right? It requires a lot of additional convention. It's really just not worth it. And if you continue to higher rank tensors, this is a 1-1 tensor. If you have higher rank tensors, you would have to represent them, say, a 1-2 tensor would have to be represented by a cube of numbers. You have a 2-2 tensor, you have a 4-dimensional cube of numbers. I mean, what's the point? Okay? It's a singular possibility for a 1-1 tensor and 0-2 tensors to come up with such witchcraft notation. Okay? I encourage you, I introduced it, and that's the tempting bit, and on this occasion we will resist temptation. Resist the temptation to think of it like this. Crap this, right? Think in terms of components, the summation rule, and always try to understand these guys from the component-free and basis-free notation. That's the task. And you need to gain some facility by practicing in switching between basis notation and basis-free notation, like I did here, by plugging in the basis. That's key. And forget about this kind of stuff. This is confusing. Okay? And I mention it because, well, it's ingrained in our thinking because we used it so often in the beginning, but essentially the lesson is don't do this. The upshot was a gentleman only chooses a basis if he must, and there's the stronger widow principle. A lady must never go to the cemetery. Okay? She should enjoy the fortunes of the basis-free notation. And in this spirit, we now look at change of basis. It was a rather longish aside. The change of basis is I have a basis and I define a new basis EA by some coefficients AAB BA EB, and I study how the components change. How do components of vectors and covectors change? Because the components are basis dependent. So it's very simple. So say you have a covector omega. This covector omega has components omega A, because you apply omega to EA, that defines the components. Choice of basis, the abstract object, you plug in the basis, you get the components. Now, however, under a change of basis, always write equal signs. EA, well, that's the other way around, can be written as using the matrix B from before. B, A, M, say, EM. That's the same guy, because we had E, A equals B, A, M, EM. And A and B were inverses as matrices. And in fact, the inverse of a matrix with index up, down, is actually really the inverse of the corresponding endomorphism and then the representing matrix. So this all fits together. You have this, and you get here BMA. This is linear, so you can pull out the numbers. You can pull out the invisible sum sign. So you have omega of EM, but this is nothing but omega M. That means if you change a basis, sorry, there's the twiddle missing here, there's the twiddle missing here, the twiddle missing here, and these are the components of omega in the twiddled basis are called omega twiddle. So if you change basis, new basis or old basis is BM times the new basis or the other way around, you get the rule for the change of components like this. Is this matrix B that you use, and you do the summation convention with the components in the twiddled system for the omega, and you get the components here. It's precisely the other way around for vectors, as we'll see. So the eighth component of a vector, how do you evaluate this? Well, that's the vector applied to a covector. And I say that's strange, vector applied to a covector. Well, this already uses, this considers here the vector as a T10 tensor, and then of course it eats a covector. The definition of this, after all, is considering the vector as an element of V, and then you can act on it with the covector. So this is this duality I showed before, because this is vector space isomorphic to V. That is this, and now you can expand the V and say that's V, B, EB in this basis, but then you can represent the spaces differently. It's epsilon A, VB, and you have B, M, B, EM twiddle. You have this. But these are numbers, those are numbers. You can pull them out because this is a covector. So what you end up with down here is VB, BMB. And here what remains is epsilon A on E twiddle M. Aha, hang on a second. Yes. And now I need to show that I can actually represent, one brief moment, please. That is this, that is that. So, and what I end up with here, okay, I hope I'm not in trouble, is epsilon A of E twiddle M. Now that I cannot expand. There's something going wrong here. V epsilon A. I apply this to this. I expand this in that basis, and this gives that. Aha. What I should have done, and would have been much cleverer, I expand the V here in the twiddled basis. So it's the twiddled basis and the twiddled components that go with that basis. That means those are components with that basis. So then I have the twiddled components here, and now I need to use this relation. I'm not using B, I'm using A. A, B, M is the E twiddle, but in terms of the untwiddled E. So now I'm in business. So I pull out the V twiddle, and this here is the A MB, and back here I have the epsilon A EM. It's my choice whether I expand this V in the twiddled or in the untwiddled basis. That's my choice. I made a better choice now for what I want to prove. Now this is because we chose dual basis is delta AM, so the result here is AMB. AM. I got the indices somehow. No, it should be fine. So an AEM, AMB. Yes, AMB VB, correct. AMB VB twiddle, and the delta makes this into an A. It's perfect. Right. So you have the relation that the VA components are the components V twiddle B from the other system, and here you have the summation convention, of course, and now it goes with the opposite matrix, with the inverse of this matrix. So if vectors transform this way, covectors transform the other way. And you can generalize this to tensors, and if you have tensor components, so C for, so this is A, this is B for the vector, and for tensors, you have the rule. So let's start in the untwiddled system. You have T A1 da da da, and then you have B da da da. Let's write it like this. There can be several. I just write out the first bit, because all that matters is whether the index is up or down. If the index is up, then you use the matrix A, and you introduce a dummy index M, and that goes with this M over here, da da da. And for an index down, an N, you use the matrix B, but then the N is up here, and the resulting index B is down there. So you have many of these A's, and you have many of these B's. And so the upstairs indices transform like vector indices would be the rule, and the downstairs indices like the others. And of course, those are the components in the new frame. And we always remember that if A is a linear map from V to V, which it is, then B is the inverse of A. That's well defined. We know what that is. That's also a linear map from V to V. And A, B are just the components of A. And B, A, B are the components of B, and those are the guys I'm talking about. And so if I say the inverse matrix, that either uses the witchcraft matrix multiplication, or it uses the notion of the inverse of a linear map, which is totally free of any coordinates, and then you represent these maps by the corresponding matrices. Of course, this relation that B is A inverse implies the matrix multiplication. So it follows, it's not the definition, but it follows that AM, B is delta AB. That follows from this inverse, but this is defined basis free. Okay. So that's the transformation rule for a tensor under a change of basis. And you see it's a little bit, you have to see where the twiddles are and the A's and the B's and so on. It's best every time you need this, if you want to explicitly know if the basis goes like this, how does the upstairs index transform, it's best to quickly rederive this. Okay? Otherwise you get probably confused. Okay. So are there any questions so far? Yeah?
Could you explain one more time how you come from V and epsilon A is epsilon A and V?
How I come from here to there? Here? From this to the next? Okay. So that was essentially, so let's, okay, it's good that you ask. So it's this little cloud. Okay. We had this fact that if I have a 1, 0 tensor over V, that's actually the same as a vector. 1, 0 tensors are vectors. But it was not so immediate. Immediate is that the 0, 1 tensors over V, there are all the linear maps phi from V to K, but that's by definition is V star. So that the 0, 1s are V star is immediate. That the 1, 0s are V is not immediate, and it's only true if V is finite dimensional. Okay. And it went like this, so elements in here are linear maps from V star to K. That was by definition. And how do you understand that a linear map from V star to K is again an element of V? Well, you realize that this is, of course, V star star. It's all the linear maps from the vector space V star into the number field. This is this. And in order to understand this, you need to construct what you have to construct on the problem sheet. Namely, on the problem sheet, you remember I said you will be asked to prove that there is an isomorphism, a vector space isomorphism from here to there. So once you did this proof on the problem sheet, it's the constructive proof, you will, from the problem sheet, understand that this, considering V as a T10 tensor, it can act on a covector, you see. If something is an element here, it can act on a covector. That's this interpretation. The V can act on the covector. Once you interpret this element in here as an element here via this isomorphism you're going to construct, that moment the covector can act on the vector. It's just the other way around. So where you saw the problem, there is a problem. And in finite dimensional vector spaces, it's solved by the isomorphism you're going to construct on the problem sheet. And now, following your question, I will add another sub-question that will make this very explicit. Okay. So you're absolutely right. It could not be understood technically from precisely what I wrote down, because I outsourced the solution of this construction of this canonical isomorphism to the problem sheet, but it's outsourced there precisely because it's so useful. So you should deal with that. Okay. I mean, usually this is just presented as, let's say this acts like this or so, right? Okay, but that's not let's say, we construct this properly. And it has to do with the slightly increased difficulty to show this isomorphism, whereas this isomorphism of the 0, 1 tensors to the covectors is immediate. This is just a thing. Here it requires further study. But it's true nevertheless, it's just not that obvious. Okay? That's the point. So this is a subtlety that's usually in physics is sometimes not mentioned. Okay. Further questions so far? Okay. Now, something we're also going to use and which sometimes comes with a lot of confusion is the notion of determinant. So let's look at determinants. So you need to trust me that the order in which I present these things, first without the basis, then the basis to get dimension, then going back to the basis-free notation, and again introducing the components on, this precise order is important to understand the whole subject. You have to understand it in this order. If you started from the beginning and you think from the beginning as a vector as a collection of numbers that are its components, then you already are on the wrong track. You need to start thinking abstractly, and only after introducing a basis you're allowed to do so. Okay, it's very important to get this order straight, because otherwise all kinds of confusions arise. And one particular thing we're going to use heavily is determinants. Now, in witchcraft mathematics, determinants, you take a symmetry of numbers and you calculate the determinant according to some mysterious rule. Okay? And once you establish this rule, you show things like, well, heavy work to show it, that actually the rows and the columns, if you exchange to rows, the determinant picks up a minus sign. If you exchange to columns, it picks up a minus sign. And it's a very mysterious rule acting on a symmetry. Okay. Now, the symmetry is not particularly meaningful. And the symmetry also hides another fact. So again, some polemics on symmetries. Symmetries. You see, if you have phi, which is a 1-1 tensor, then you have these components A, B, and you may think of them as being here ordered according to the row and column rule. Now, unfortunately, if you have another tensor, which is a 0-2 tensor, what's a 0-2 tensor? Well, a 0-2 tensor, if you write down the components according to our rules, it has indices downstairs. Why do the components have indices downstairs? Well, because the 0-2 tensor actually eats two vectors. That means it eats, in particular, the components eat two basis vectors, but the basis vectors have the indices down, so the components have the indices down. Then you can arrange this again according to the row-column rule, that then looks somewhat like this, GD1 and GDD. Now, this is an endomorphism, or a 1-1 tensor, and this is a 0-2 tensor. Sometimes people call this a bilinear form. Endomorphism, bilinear form. Entirely different beasts. In particular, this one has an index up-down. The index up transforms with an A, the index down with a B matrix under change of basis. This guy transforms with 2 times a B matrix. In mathematics, you see transformations of this type. You say you take the A matrix and you come, okay, how does this, it looks somehow like this. You say transformations look like this. And here, so also in mathematics, you write transformations look like A transpose GA. I'm sure you saw this. You saw this as a transformation rule in linear algebra, and you saw this as a transformation rule in linear algebra. There's the inverse, there's the transpose. I wrote transpose before like this. Now, the transpose, as I showed you before, is a concept from witchcraft mathematics, okay, from symmetry mathematics. This is slightly better. And the difference between this is the transformation rule, if you want, for an endomorphism, and that's the one for a bilinear map. For the components of a 1-1 tensor, for the components of a 0-2 tensor. Two totally different objects transform totally different under change of basis. Now, if you do not change basis, you might delude yourself into thinking, this is a matrix, that's a matrix. What I can do with a matrix, I can do with a matrix. So in particular, I could say I define the determinant for this matrix according to some witchcraft rule. Well, then I can take the determinant of that matrix down there as well. No, no. Determinants are only defined for endomorphisms. How can I see this? Well, I have to do it basis free, then I can see what goes on. Very important. Okay, so let's okay. I think I stay here for a moment. So, so first we need a definition, and the definition is the following. On a dim V equals D dimensional, also so finite, dimensional vector space, V, an N form is a 0 n over V tensor, 0 n tensor, let's call it omega, that is totally antisymmetric. Totally antisymmetric. What does that mean? Well, so first of all, yeah, so the n must be somewhere between 0 and the dimension of the vector space. The case for 0 is, okay, so special, let's first do the case n non-zero, n greater than 0, and the n equals 0 case comes in a second. N greater than 0 is you have an omega, and you plug in, if it's an n form, it eats n vectors. So I can plug in the vector v1 down to vn, because it's a 0n tensor. But it has a special property, and the property is that the result of this is the same as if you took a permutation of these vectors. So you map the 1 by a permutation pi to another number, to the 7th, say, v pi of 2, v pi of n for any permutation, pi in the permutation group as n. So that's not the sphere, this is the permutation group. But then you have here a signum, a sign of the permutation. And you know the sign of a permutation is +1 if it's an even permutation, it's -1 if it's an odd permutation. I trust you know this. More simply said is, if you exchange any 2, you pick up a minus sign. If you change another 2 or the same 2 again, you pick up yet another minus sign, so you don't pick up a sign. So a totally antisymmetric 0n tensor is called an n form. And this antisymmetry is wildly important. And the case n equals 0, that is just, omega is then just a number. Okay, so a 0-0 tensor, I should have said this before, I had the 1 zeros, the 0 1s, the PQs, and the 0-0 tensor, by definition, by convention, is the underlying number field, or a scalar. That's just convention, and so that is plays out in particular here. And of course, if there's no entry, the symmetry condition doesn't have an effect. Also, if it's a 1 form, a 0-1 tensor, the antisymmetry condition has no effect because there's nothing to be exchanged. Okay, so that's this. And then a special case of this, a special case are the so-called top forms. Top forms. What's so top about the top forms? The top thing is they have the top rank. you have a form that has as many entries as your vector space has dimensions. Couldn't you consider a 0 d plus 1 tensor? You can. There are tensors that have more entries than the dimension of the vector space, right? But if you then require them to be totally antisymmetric in this way, then you will, if you plug in tensors, they will always be linearly dependent because you have more than dimension many, and then the antisymmetry actually will kill the whole thing to 0. So you could drop this restriction that n must be less or equal to the dimension to have a form, to have an n form, but all the higher n forms would be 0. So we don't consider them. And the highest rank form, hence the top form, has the rank equals to the dimension of the vector space. Top forms have the following property. If omega and omega prime are top forms, then there exists a number c such that omega prime is c times the omega, if they're non-zero. Top forms, both non-vanishing. That means essentially up to a scalar multiple, there is only one top form on a vector space, constructed over a vector space. Okay, that's very, very easy to see because it's totally antisymmetric. It can only differ by a factor. Okay, so choice definition, choice of one top form, omega. And you see the choice isn't big. You can choose one, another one is 5 times the one you chose. It's not a big choice. Choice of what one top form is called a choice of volume form, of volume on the vector space. Okay, why is this? Well, because you make the next definition, let V1 to Vd be d vectors on a d-dimensional vector space V, then the volume spanned by V1, by them, is, well, let's call it volume that's spanned by these vectors V1 to Vd, the order matters, is simply defined as omega of V1 to Vd. So what happens if you have, in a 3-dimensional space, you have 3 vectors. If you plug them into your choice of volume form, that will give you a volume. Okay? If if the 3 are linearly dependent, if they lie all in one plane, then the antisymmetry will kill it. Of course, if the 3 lie in one plane, the span volume is 0. They need to be linearly independent to span a volume non-zero. And the same is true in higher dimensions. But in order to assign a volume, you need to choose one such top form. So you might have thought that volume is like you need an inner product or so, because you need an inner product to have angles and lengths and so on. But volume is actually a choice of a top form. That will come back in the lectures. We'll need this at some point. So that's one place where you need the volume form. So if you wish, a vector space together with a choice of top form can then be called a vector space with volume. So it's additional structure you choose, but all your choice is in the factor. Now, what is a determinant? Definition. So first of all, there is no determinant on a vector space without a volume form, but it's not that bad. We'll see in a second. Definition. Let phi be an endomorphism. And for an endomorphism, or for, I emphasize again, for finite dimensional ones, for a 1-1 tensor, or emphasized again, for a map V to V linear, and so on, for an endomorphism, we define the determinant of the endomorphism. It's not the determinant of the components. It's the determinant of the abstract object. And that's a number. That's a number. And this number is defined as the quotient of, you take a top form, omega, and you use a basis, phi E1 to phi ED, we're d-dimensional, and you divide by omega E1 to ED for some volume form omega and some basis E1 to ED of V. And of course, if I say for some, I need to check whether this is well defined. Well defined, that means is it independent of these choices? Independent of these choices of which omega you choose and which basis you choose. Now, you immediately see why it's independent of the choice of omega. Do you see that? Who can tell me why it's independent of the choice of omega? Exactly, the factor C, as we call them. So two different, I mean, it's one omega. Another omega gives you a factor C, but they cancel. Exactly. So it's independent of the volume form omega. That's immediately clear. That it's independent of the basis you show by plugging in the basis change we had before. You plug it in here, you plug it in here, you pull it out, and so on, and you'll find it's independent of that too. Because essentially you get the omega of the basis change matrix here survives, and those factors cancel as well. So in fact, yes, it is well defined. Yes, check. I'm not going to do this right here. Now you see why you need an endomorphism, because you have a vector, but you need to produce from this vector a vector again. Very important. Now you can read off a few other things. I mean, we know that the determinant of this phi, of course, it will coincide with the determinant, according to the witchcraft rule, if you apply it to the symmetry for phi, for the symmetry arrangement of its components. I mean, what you learned is correct. The determination rule, okay, will coincide. And the determinant to what order, to what power of components of phi appear in the determinant. So if you have an n times n matrix and you calculate the determinant, what kind of products do you have in this determinant, in the number that comes out? Well, it's the power of the dimension of the vector space, right? I mean, you have these so witchcraft rule is you have the determinant, the witchcraft determinant of the representing matrix A, B, C, D, say, and that's AD minus BC. So it's a 2 by 2 matrix, and so you have factors of 2. If you have a 3 by 3 matrix, you have ADM or whatever, ADM minus, and then come all the other products. There's always this power. Well, you see this here, because every phi E1 gives you one component of phi, right? With a vector again, and then the omega eats d many of those, and that is why the corresponding powers appear here. But now other rules, like what happens even in a big representing matrix for phi, so expand in some basis, what happens under an exchange of row and column, of two rows and two columns and so on, right? You can read it off from here, because the omega is totally antisymmetric. So if you change rows and columns in phi, you keep the order of the bases. Only up here there will be one switch of row and column up here because it's in the representing matrix of phi that picks you up a minus sign because the omega is totally antisymmetric and so on. So all these rules follow directly from here, and this is the abstract definition. Now, it's also clear what happens under a change of basis. Well, we already said that because we said for some base, under a change of basis, nothing happens. And that is in witchcraft rules, is this that the determinant of, so here you have the symmetry representation. You say you change the basis. You remember that in an endomorphism, you change basis like this. I erased it. And you say, but that's the same as the original determinant of the symmetry, right? If you have this A inverse, and well, you know that works like this. You can also show that the determinant of the composition, so take the determinant of the composition of two linear maps. This is not a matrix product, it's a composition because the determinant eats an endomorphism, totally basis free. That can be shown to be the determinant of one endomorphism times, but that's the times in the multiplication in K, times the determinant of the other endomorphism. And that also follows here simply from looking at compositions and so on. So all the standard rules, right, come up in this way. Okay. So now why did I emphasize so much the difference between bilinear forms, bilinear maps, not forms, sorry, bilinear maps and endomorphisms? Well, because in physics and also in mathematics, one has opportunity to also use the determinant of a bilinear form. And that will also be on the problem sheet, but I'll show you the basic idea. So again, there is no doubt that the determinant as it is defined can only be defined for an endomorphism because you need to produce vectors here again. Problem sheet speaks of the following. So again, the witchcraft version, which we're trying to replace by a better version on the problem sheet. The witchcraft version is this, so we're only talking about matrices now. You have for an endomorphism, you have the representing symmetry. Yeah? And you know it's the same as this rule for changing bases. And you have the rule for determinants that this is that A inverse A, also that A inverse, that phi, that A. But then these are numbers, so you can push this here, and then you can use the rule backwards. Is that A inverse A times that phi. And of course, this here is the unit matrix. Now, or the unit endomorphism, that's it. But if you have the unit endomorphism, you of course get 1 for the determinant. It's also very clear from this definition. So the whole thing results in that phi. That means determinants do not depend on the choice of bases. Well, they better don't. We manifestly define them this way, but this is the witchcraft version to show this. Okay. So this is not a big result of the witchcraft definition of the determinant. It's an important consistency check that the whole thing doesn't depend on the choice of basis. But now we do something different. We calculate, according to the witchcraft rule, the determinant of a bilinear form. So of a 0, 2, not form, of a bilinear map. So of a 2, 0, 2 tensor. Okay? Whereas here, this was an endomorphism, a 1, 1 tensor. Okay? Now, So this is the witchcraft definition, but it coincides with the proper definition. Now this is the witchcraft definition, and it cannot possibly coincide with the proper definition because the object here needs to be an endomorphism, and I now act on the representing matrix. It's illegal. It's deeply illegal, okay, from an abstract point of view. But if you do this, you can check what happens under a change of basis, and I showed you before, witchcraft calculation shows you this is A transpose GA. That's correct, because you come from the left and you come from the right. That's what the transpose does. And if you calculate this, this is det A transpose det G. Now, the determinant of a transposed matrix is again the matrix, the determinant of the matrix. You know that too. So what you have here is the determinant of the matrix squared times the determinant according to the witchcraft rule. So question, is the determinant of a bilinear map, is that independent of the choice of basis? The answer is no. It will pick up a factor determinant of the change of basis matrix squared. It is not well defined. Now, hence, we wouldn't use it. But it turns out, and that's the trick, we do something ill-defined from an abstract point of view, but in other places, there will be factors like this coming up in the denominator. So there will also be not well defined under change of basis, but then the product of something that in this fashion is not well defined under change of basis and something that picks up the opposite factor, the product will be independent of a change of basis. Okay? And hence, one starts considering these guys. And now you say, okay, so what now? If it abstractly cannot be defined, you commit, say, a mistake, and later on the opposite mistake, and the mistakes cancel. How can we cast this into proper mathematics? And the answer is we can by considering bundles. Because we will consider basis changes, we will consider a bundle where you have the basic manifold you're interested in, and as a fiber, we will attach at every point the transformation group that you have here for a change of basis. It's called a principal fiber bundle. And using this principal fiber bundle, we'll then be able to give a bundle definition of what a tensor is, and that will work. And we'll give a bundle definition, that's the keyword, what a tensor density is. And the density picks up this, but we can do it without this hand-waving mathematics. In the bundle formalism, all of this has its place. That's one of the big reasons why we need bundles.